Okay. You see the PDF, yes?
Yes.
Yes, doctor.
Yeah. So we have done all of these. Okay. So now we will start the problems on the distributed load. Replace the distributed loading with an equivalent resultant force and specify its location on the beam measured from point A. So as you can see, it's the same type of questions. I have a certain load. I want to reduce it to 1/4. So always I should follow the same steps. First step, I choose any point on my beam and I reduce to this point. Then I move my force in a way to produce an equivalent moment. Here, since they asked from A, maybe some of you will say, let us reduce at A first, okay, and then find the distance. But do you see a black screen now? Okay, so you can say, let us reduce at A because the distance we want to move is from A. You can do this, but you should pay attention when you do this because look, when you take point A, I will do it with you. Not all couples, not all forces will have same moment, same sign of moment about A. Some will be rotating clockwise, other will be rotating counterclockwise. So you just should pay attention for this, okay? Let us do it to practice on it. But even if they said measured from point A, you can't reduce first at O. Then when you find the distance from O, for example, let's say here you got, let's say this distance 5, for example, you say then the distance from A is 5 minus 3. So when they say measured from A, this does not mean that you should take resultant system at A. You can choose, still you can choose O, okay? But let us do it to see what will be the difference. If I want to reduce at A first, the first step here is to divide my distributed load into several parts, okay? I have first, here I have a triangular load. So I will start with it. This triangular load can be reduced into one force. This force first should be equal in magnitude to the area of the triangle, okay? And the area of the triangle is 15 times 3 over 2. Okay, so I have 15 times 3 over 2. So it is 45 over 2 equals to 22.5. Now, concerning the point of application, you know that the centroid of your triangle is somewhere here. So we said that it should be at 2/3 from the base, from the point, and at 1/3 from the base. So here, this distance will be 2/3 of 3. So 2/3 of 3 is 2. So it's 2 over 3 times 3 is equal to 2. So now you know that your force is acting at 2 meters from the origin. And since you are interested at point A, then you can say that this distance from the base will be 1, okay, but because it's 1/3 of 3, so this is 1 meter here. Now, we are done with the reduction of the first force. Okay, let us move to the second one. Here you have a trapezoid. So whenever you have a trapezoid, you can do two things. Or you should remember the formulas for centroid of a trapezoid and area of a trapezoid. Or what I find easier is to divide your trapezoid into two parts. One, a triangular part, and a rectangular part. Okay? So for the rectangular part, here, the area will be, you have that the length here is 10 kilonewton per meter, and the length here is 3. Okay? So for your rectangle, you have 10 times 3 it is 30 Newton. So this force, the force of the rectangle, will be equal to 30. And it should pass by the centroid of the rectangle, so just at the middle. So this is my second force, okay? And it's at 1.5 meter from A. So the distance here is from A is 1.5 meters. Okay, now I still have the triangular load above here, this small one. So for this one, what is the area? First, what is this height here? The height here is 15 minus 10, okay? So the difference between is it is 5. The height is 5 and this is 3, okay? So the area of the triangle is 5 times 3 over 2. So it is 15 over 2, 7.5. And concerning the point of application, as we said, it's a triangle. So G is at 1/3 from the base. This is the base. And the total base height is 3 meters in length. So at 1/3 from the base, it's 1 meter. So it is acting at 1 meter from A. So I move 1 meter from A, and I put the equivalent force of the triangle, which is equal to 7.5. Okay, and here of course it's you can just put it at the beam because it's applied at the beam. Okay, so it's 7.5 located at 1 meter from it. Okay, you still have only one triangular load. For this triangular load, you have first the magnitude is equal to the area. The area is 10 times 3 over 2, so it's 15. And it's acting at from B, the base is at B, okay? It's acting at 1/3 from the base, so it is at 1 meter from B. But since we are interested to reduce at A, we should find the distance from A. So this is 1 meter from B. So from A, it will be 3 plus 1. It will be at 4 meter from A. Okay? Now, once I reduced my distributed load to several concentrated forces, now I can reduce my system to point A. Okay? The figure is a little bit confusing. This is why I will draw it for you again. So this is your beam, and point A is here. Okay? So what you did is that you simplified your system. You reduced it into several concentrated forces. The first one is at left of A, and the distance from A is, as we have seen together, is 1 meter. So here you have 1 meter from A, and the value of your force is 22.5. The second force is replacing the rectangular one. It is at 1.5 meter from A, so this is 1. Now you have 1 and 1.5. 1 is for the triangular load اللي هي 7.5 kilonewton per meter. So this is the triangular load. This is the rectangular load here. And you know that this distance is 1 meter. This distance is 1.5. And the values are for the triangular 7.5. And for the rectangular, it is 30. And finally, you have the final force of 15 kilonewton. Which is the farthest one from A. So this is 15. And I have a distance of 4 meters. Okay, so now it's like the problems we were doing before. We want to reduce to A. Okay, so what we do first, we do the summation of forces to get the resultant force, which will be equal, Fr is equal to 22.5 plus 7.5, 30, plus 30, 60, plus 15, 75. So you can get here the same result, which is resultant force. Now for the moment about A, just pay attention. Choose a positive direction. Let's say you consider the clockwise. If you consider the clockwise as positive, you have the forces, the three forces at the right of A are doing clockwise moments, while the one at left of A is doing counterclockwise moment. So what will be your total moment? M resultant at A, M resultant at A is equal to first plus 7.5 times 1 plus 30 times 1.5 plus 15 times 4 and minus 22.5 times 1. Okay, so now once you reduced it to 1/4 1 moment at A, okay, you can say that I can replace the system. So now I end up with this. I end up with a system at A having a downward force and a clockwise couple. Okay, so how can I get rid of the clockwise couple? I should move the force a certain distance d to produce from A to produce the same effect. I should of course move it to the right to produce a clockwise moment. And what should be the distance to move? The distance to move should be in a way that Fr times d equals to resulting moment. Okay, so d will be equal to m resulting at A over Fr. Okay, any question on this?
Doctor, at the
Yes.
start of the question you told us إنه أوقات فينا ناخد origin وأوقات فينا ناخد point A.
Yes, you can, because look, هنا they want the distance from A. But أنت when you reduce, let's say you reduced at O, okay? When you do your work, then you will find the distance from O. But after finding the distance from O, what is D? D will be the difference, okay? So let's say you calculate the distance from OD prime, okay? And you know that between O and A, what is the distance? The distance is 3 meters, okay? So this is 3. So you can relate D and D prime easily. You can say that 3 plus D, okay, is equal to D prime. So once you find D prime, you can say that D is equal to D prime minus 3.
Hey, did we only do this so we don't get a negative moment?
Yes, ساعتها كلهم بيكون عندهم clockwise moment about O. So maybe it will look easier for you. But at the end, you will get the same result. Okay? Try to do it about O and you will see that you will get the same result. So here, as you can see, as we did, they reduced the system to several forces, as you can see here. And then they displaced the force from A in order to get the same effect. Any question on this? Okay, so we'll continue some problems on distributed load next time, and then we can start a new chapter.
Thank you.
Welcome. Bye-bye.
Bye, doctor.
Bye.